Hello, chemistry students. I'm coming to you today from my homeschool room in my house, since we could not be together today. I thought it might be helpful if I just recorded what I would have said today in class, and that way you can still access the information, practice the problems, and be on track for next week. This is Module 7, Atomic Structure. Basically, this is what's inside these things called atoms. You probably already know it, but remember, there was a time when nobody knew it. All that had been done was that Democritus had hypothesized that stuff is made of smaller stuff. And that's the burning question, is what is the smaller stuff? So there were a few nascent experiments that were done. In the beginning of the chapter, it talks about them. You don't really need to know the details of the experiment, but I would like for you to be able to follow them through logically and say what was the major change in atomic structure models that came out of each one of the experiments. At the beginning of the chapter, we see that particles that comprise all the known elements are somehow alike. All that means is that calcium is made of some particles, nitrogen is made of some particles, oxygen is made of some kind of particles, and that those particles are the same, even though the calcium and the nitrogen and the oxygen are all very different in terms of their properties. So then we start talking about the behavior of the particles. And what is known at this point in history, that we're talking about a long time ago, is that somehow the particle charge is involved. There's a charge issue. At this point, they did have access to electricity. They could run charges through gases and see what happened. We'll just review it real quick. You know that like attracts the opposite. So positive and negative charges attract. Positive and positive repel, negative and negative repel. And if you have equal positive and equal negative charges, you get a total net charge of zero, what we call neutral. And that was all known. So the big mystery was, how are charges involved in these atomic particles, and how do they behave? So the first experiments were done with gases and these charged particles, and basically that's where we get electrons being discovered. Protons were then hypothesized, because if you have a negative charge, you must have a positive charge in order to have a neutral atom. So they knew about protons and electrons. Neutrons hadn't been invented yet. They hadn't been discovered yet. So one of the first things you have to do in this chapter is figure out how many protons and how many electrons are in a given atom of something. So I'm looking at, on your own, question 7.1, how many protons and electrons are in the following atoms? The first one is chromium. So the first thing you want to do is look up chromium on your periodic table. I have Celeste's eliminated periodic table here. Chromium, is it working? Celeste is my technical assistant. Celeste, where's chromium? (24). There it is. Chromium is atomic number 24. So it's, I don't know if you can see, but it's in this area. It's right here in the first row, right next to manganese. Okay, chromium has an atomic number of 24. What does that tell us? What that tells us is that chromium has to have 24 protons and 24 electrons. This is really basic. You can do it for anything on the chart. You just look for the big number that's on top of the element symbol. Manganese, 25. 25 protons, 25 electrons. Let's leave that for there. That's pretty good. Now, let's talk for just a minute about isotopes. You've probably heard the term. You may not really know what it is. Basically, an isotope exists, and it's got the same number of protons and the same number of electrons as the one you see on the chart. The only thing that's different about it is it has a different number of neutrons. So neutrons have no charge. The charge of the atom is not going to change when you increase or decrease the number of neutrons. What is going to change? Remember, neutrons have mass, just like protons do. So it's going to be heavier if it has more neutrons. But otherwise, it's going to be exactly the same in terms of protons and electrons. What does that mean, that it's heavier? Well, it's going to behave differently depending on the isotope, it could behave very differently from the regular version. Now, the author of our book goes into a bit of detail about how isotope is a relational term. You don't want to hurt anybody's feelings by saying that they're not normal. Carbon-12 is normal, but an isotope of carbon that has more than 12 neutrons is not normal. He says that that's going to hurt carbon's feelings, so we're not going to say that one isotope is normal and the others are abnormal. They're just different. They're just all different and yet all the same. Isotopes are useful. They are incredibly useful in biological research because of that slight difference in mass. They can be separated. They can be tagged and followed in experiments. I used to use radioactive isotopes, not the scary kind, really just minimal protective gear needed, to track proteins in an assay. It was super cool. Okay, what if you know, let's see, the examples are 7.2 on page 208. What if you're given the number of an isotope and asked to determine how many protons, how many electrons, and how many neutrons it has? So I'm looking at example 7.2. The example that's given first is argon 40. This is how we write argon 40. We write the 40 as a superscript and then the symbol, but you say it argon 40. So what do you know? What does the 40 tell us? Well, the 40 tells us how many total we're going to have if you added protons and neutrons. So this is a little bit confusing. I think the best place to start is to look up argon on the chart, on the periodic chart. Argon is, where are you, argon? Argon is number 18 on the periodic chart. It's right here, argon 18. So remember what we just talked about a minute ago. Regular argon, normal argon, just kidding, normal argon has 18 protons and 18 electrons. But this isotope of argon has 40 written in front of it. So then you would take that number 40 and you would subtract the number of protons and you get 22. What this number means is that's how many neutrons argon 40 has.